This is just such a weakness at the school, right? We don't have you give it to them like, oh, I want this.
Go ahead. Can you hear her say this meeting is being recorded?
Yes, we can.
Oh, okay. That's kind of what I figured. How are y'all doing? Are y'all ready for this semester to be over?
Very ready.
Maybe.
Yeah.
Yeah, I'm ready for this semester to be over. I'm ready for this class to be over. This class has just been a real challenge for me. I think I told you all at the beginning, and I'll remind you, for some reason, despite having gotten a PhD in physics, I never took this course. I never took a graduate level mathematical methods in physics course. Of course, I used a lot of math in my research and in a lot of my advanced physics courses, but I never took this course. So finding out how this was organized was kind of it was weird. And when I surveyed, classes across the country, every one of them was distinctly different from every other one. No one agrees on what you need to cover. So at any rate, we'll coast to the finish line over the course of the next 2 lectures, and then we'll go on to GR next semester, which should be fun. Okay, so I'm going to pace myself. I'm going to try and not go too fast. I hope that I am fixing that stupid extend-a-mark thing. Madison, what you said was not my problem because I'd already deactivated the touch on the screen. So that I had actually tried to address. I think it's because I had it plugged in to a charger, which is slightly over the voltage. And I think that's doing it, but we'll see.
I also heard from someone that you may just need to clean the screen, like if there's weird debris on it, that could cause that.
Okay, well, I'm not going to clean it right now. But anyway, yeah, I hope it doesn't happen. It doesn't happen to me while I'm writing my notes. It's just when I'm doing this. But anyway.
You should also be able to change the sensitivity in the settings somewhere.
Okay, I'm just going to give the damn lecture if that's all right with you guys.
I mean, you could do that.
I'm going to mute you if I can find you. I'm not going to mute you anyway. All right. So I am, the stuff I'm throwing at you can be a little abstract, and I can take big steps, but I'm going to slow down a little bit today, and I'm going to hopefully impart some skills in simple things like integration to you, because there's these huge steps where I could say, and now we integrate, and I'll show you what the answer is, but unless you actually understand the steps in the integration, it can kind of suck. So we won't get all the way through this chapter today. There's a lot of stuff on Green's functions that we won't cover, but I'd rather just show you things in detail, and then you can always finish up studying the chapter for stuff as you need it in your other classes and research. Okay, so we finally found the Green's function at the end of last lecture for this second order linear differential operator, d by dx squared plus a d by dx plus b. And we found the Green's function for it. And to find the solution to the equation, and of course the equation that we were working with was L on y equals f of x. In order to find the solution for that, we're going to use the Green's function integrated paired up with the function f on the right, but we need to add in initial conditions. And so one of the first things we want to do is we want to find a solution to the homogeneous equation, which is that one. And these are actually relatively easy to find, so I'm not going to walk you through it. I'm just going to write them down. But we would find 2 solutions, y1 of x, y2 of x. And this would be e to the minus a over 2x, e to the minus a over 2x times the sign. I don't know why that thing keeps go away thing. Yeah, thank you. Do you keep seeing this green screen descend from the top and then go back up? Okay, never mind. If you're not seeing it, it's fine. It's hard to figure out what you're seeing versus what I'm seeing versus what the universe is going to see when I post a video of this, but whatever. Okay, so here we go. So those are our homogeneous solutions, and then we can just add those in to satisfy the boundary conditions. And so for our final solution for y of x, and remember L, it's d2 dx squared plus b d by dx, or sorry, plus a d by dx plus b. So our final solution is going to be a times the solution y1, where a is some arbitrary constant that we would use the boundary conditions to solve for, plus b y2x plus, and then here we go with the integral of the Green's function, which we found, e to the minus a over 2, x minus x prime, over the square root of b minus a squared over 4 times the sine of the square root of b minus a squared over 4 times x minus x prime. And again, that Green's function is integrated with the forcing function on the right-hand side of the equation. And then the whole thing is integrated with respect to dx prime. Okay? So now what I'm going to do is I'm going to transition my variables to make this into something which is a little more familiar to you, hopefully. And it's actually the form that he used in the book.
Is that supposed to be from x naught to x naught?
Oh, no, it's not supposed to be from x naught to x naught. It's supposed to be from x naught to x. Thank you. That was done on purpose by me to see if any of you would notice. And thank you, Josh, for noticing. Man, good Lord, that's awesome. Not.
Do
Anyway.
I get any like good boy points?
Yeah. I'll give you a 0.001 participation points.
Nice.
Thank you. No, thank you. Seriously. Okay. So what we're going to do is we're going to take this guy and we are going to make the following substitutions. Instead of y of x, we're going to consider x as a function of t. And then instead of the coefficient a, we're going to consider the coefficient 2 gamma. And instead of the coefficient b, we're going to consider omega naught squared. Okay. Now, what this does is it transitions our differential equation into something like the following: d2x dt squared plus 2 gamma dx dt plus omega naught squared times x of t equals f of t, which might be recognizable to some of you. Does anybody realize what kind of situation this differential equation describes?
A damped harmonic oscillator.
Well,
damped forced harmonic oscillator.
Yes, a damped, this is the dampening term, and forced harmonic oscillator. Okay. So, you know, he derives everything that I did in this notation, but I don't want you to get stuck on the idea that will only work for functions of time, or it will only work for damped forced oscillators. This is just one realization of it. But let's explore this a little bit. And so let's see. So first of all, let's assume that the f of t function that we're going to use, and I'll maybe do this, is 0 for t less than 0. And then we're going to take it to be a dying exponential, e to the f naught e to the minus alpha t. For t greater than or equal to 0. And let's go ahead and assume that the object that we're studying starts at rest in equilibrium. Okay, so at t equals 0, we want everything to be at rest and at the equilibrium position. And so this is going to go ahead and fix these coefficients to be 0. So the only part that we have to deal with is this complex part. Okay, so in this case, the solution is going to turn out to be, and I'm just going to rewrite this in terms of these substitutions. It's going to end up being, and let me find the best. I don't want to write the whole thing. Okay, I'm going to write it like this. I'll skip a step, but there's the intermediate step in my notes. E to the minus gamma t times f naught, integral from 0 to t of 1. Oh, no, don't do that to me, man. Don't do it. Okay, 1 over the square root of omega naught squared minus gamma squared. Obviously, that's a much prettier root than this guy up here because of exactly of this substitution. A is 2 gamma. Sine of the square root of omega naught squared minus gamma squared times t minus t prime times e to the gamma minus alpha of t prime integrated over dt prime. Okay, so I know that's a really heinous, nasty looking expression, but just squint your eyes and realize what it's describing. It's describing a function of time, t. So look at where t appears. T appears here, and it appears as the upper limit of integration. That's where the time dependence on the left-hand side is coming from. Oh, sorry, and it appears out here. However, to get this, you're integrating over dt prime. dt prime happens here, and it happens here. It only happens in 2 places in the entire expression. So when you want to do this integral to find the final form of this, you're just integrating basically a sine of something times t times the exponential of something times t. How many people know how to do that integral? Raise your hand if you know how to do that integral. Put your hands down. Now raise your hands again. No one's raising their hand. Okay, yeah, so this is why I said I want to take some time and I just want to walk you through how to do these integrals, because in the book he's just like, and then we integrate, bam, here's the answer, which I think is ridiculous. You got to show you how to do this stuff. So I'm going to start with a slight detour because this is another integration skill, but it will feed into what I'm going to do. So imagine that first and foremost, I asked you to integrate this function, x squared e to the kx dx from a to b. How many of you know how to do this integral explicitly, not look it up? Raise your hand. I got 2, 3, 4. 4, okay, so that 4 is a small portion of the class, so I'm going to do it for you, but I'm going to do it kind of quickly so that we can in turn use this result in evaluating that previous integral. So basically the thing you want to do is you want to integrate it by parts, because if you integrate it by parts, what you can do is you can replace one of those terms by its derivative and then kind of keep the other term or replace the other term by its integral. And you know, hopefully in the integration by parts scheme, the terms at, well, I'll just get going. I'm not going to say it in words. I'm just going to do it. So here we go. So the first thing we're going to do is we're going to write this with an clever insertion of the number 1. Okay. Just remember all 1 over k, but that's to let me slip a k inside of there. And now what I can do is I can say, okay, this is the derivative of e to the kx. So this is really and truthfully something like this. Okay. And so I have the integral of a function times the derivative of a function, and then I apply integration by parts to that. And I hope to God you all know what integration by parts comes from. Integration by parts just follows from, oh, the product rule in calculus. Okay, if you integrate all 3 of those terms, that's the integration by parts. It just follows from that. Okay, so we can replace this with 1 over k times x squared e to the kx evaluated between a and b minus 2 over k times the integral from a to b of x e to the kx dx. Okay? Everybody on board? We're on board? Good, good. And now we can repeat the procedure for this thing, okay? So repeating the procedure for this thing, what we can say is, all right, if I write this in the same way, k integral from, or sorry, 1 over k. Oh goodness, where's my damn eraser? There it is. Oh, part eraser, go and erase, stupid thing. Okay, 1 over k, xk e to the kx. Then this is just going to give me 1 over k, x e to the kx, evaluated from a to b, minus 1 over k, integral from a to b of e to the kx. Now, that last integral, I'm pretty sure you all can do. Integral of e to the kx, right? Yeah, you can do it. You can do it. I have faith. Okay. So in the end, this thing is going to give me integral from a to b, x squared e to the kx. So this is equal to 1 over k, x squared e to the kx, evaluated from a to b. And you can just plug in a and b for x and get those evaluated quantities. There's no real weird integration or anything you have to do. So I'm not going to plug those in. I'll just leave them like this. Yeah. So yeah, plus 2 over k cubed e to the kx from a to b. Okay, so there you go. That's the integral of x squared e to the kx from a to b. You just are doing these evaluations. Now that is straightforward. Now what I want to go back and consider is the following integral, the integral from a to b, and I'm just going to make this simple. I'll say sine of omega x times e to the kx dx. Okay. Now, will the strategy that I used in the previous integral work for this one?
No.
No, yeah, because there's no amount of differentiating sign which is going to get rid of that as a function, like it did with the polynomial. Okay. However, if we follow that road, we will find a result which will actually let us evaluate it. We just might not suspect it going into it. So let's do this. Let's just start with the same steps. So here we go. I'm going to do 1 over k, integral from a to b, sine of omega x, because we still have that e to the kx to play with. So this is going to be 1 over k times the quantity sine omega x, e to the kx, evaluated from a to b, minus omega over k times the integral from a to b of cosine omega x, e to the kx dx. Okay. And now this guy, we can take him and say, all right, if I write it as 1 over k, well, I'll just quickly write it, 1 over k integral from a to b cosine omega x, k e to the kx. Oh man, it's doing it again. Oh well, you're going to have to hear me whine about it again. Okay, so this is actually going to give me 1 over k times cosine omega x e to the kx, evaluated from a to b, plus omega over k, integral from a to b of sine omega x, e to the kx, dx. Okay? Now, does anyone see anything advantageous about what's written on the screen?
Yeah. The thing we can do now is that because essentially we have sine, we start off with sine of omega x k e to the kx, and we end up with quantity in brackets, which we can evaluate easily, and then plus another copy of the integral sine omega x e to the kx, obviously with coefficients on there, so we can move the sine of omega x e to the kx on the right-hand side over to the left-hand side.
Exactly. So this guy is just a copy of what we were trying to integrate in the first place. So we can move him to the left-hand side of the equal sign, factor out the coefficients and divide them over to the other side. And so at the end of the day, what we end up with is the integral from a to b sine omega x e to the kx dx is equal to 1 over 1 minus omega squared over k squared. Okay, you're going to get an omega squared k squared from this term because it's got omega over k from this integral, but it's also got the omega over k from this, and those are going to combine. But at any rate, here you go. Dang, that's really annoying. All right. Okay, are we on board? Everybody understand the step that Ross just described and I kind of wrote down the result of? Okay, if you don't, it's written up in a little bit more detail in my notes, but I don't want to keep on writing here, okay? So now recall that this is the integral that we were trying to do in order to find the position as a function of time. So it's basically the integral that I just did, except, you know, there's some extra stuff in there. So if we take that and we apply it to this function, then what we're going to end up as the solution to this forced damped harmonic oscillator is x of t is f naught over the square root of omega naught squared minus gamma squared times the sine of omega naught squared minus gamma squared times t minus an angle delta. That's just a shift angle, but you are going to get to, on your homework, figure out the details of this expression, which are not entirely trivial, but they largely use the result of the integral that I just did, plus a few shifts due to the redefinition of things. Okay. So there we go. There is a solution to the forced damped harmonic oscillator, which was described by the differential equation that we wrote earlier. Now, let's explore this for a moment to see if this thing makes any damn sense. So for instance, we can take gamma to 0. That is, we can remove the dampening. And if we take gamma to 0, then this simplifies to f naught over omega naught sine of omega t minus delta over the root of omega naught squared plus alpha squared e to the minus gamma t plus f naught over omega naught squared plus alpha squared e to the minus alpha t. And now what we can do is say, well, you know, what if we take the long, the t goes to infinity limit of this? If I take the t goes to infinity limit of this, well, that's just going to give me f naught over omega naught sine omega t minus delta over the square root of, oh, sorry, hold on. This was not supposed to be in there. My bad. Quit. Yeah, gamma was 0 over omega naught squared plus alpha squared. What kind of motion do you think that's describing? X of t basically is sine omega t. Anyone identify that?
So
Okay.
it's oscillatory motion.
Yeah, it's simple harmonic motion. I mean, look, we took out the dampening. We remember we had the force of the oscillation die off as we go to t equals infinity. So we started out at rest, we gave it an oscillatory force, and then we took the force away. What are you going to be left with? The thing oscillating. Okay? So does this limit make sense? Okay, I'm going to take that as yes. So this is my simple harmonic motion solution. Okay, so now I want you to remember that, well, I mean, I mentioned last time that when we're doing Green's functions, remember we want to basically try and find something which will satisfy this condition. And then we'll use it in something like this, where the Green's function itself only depends on the operator L. It doesn't depend on the function that you're putting on the right-hand side of the differential equation, okay? And I finished up last time by mentioning that, well, it doesn't just depend on the operator L. The Green's function doesn't just depend on the operator L, but it also depends on the boundary conditions that you're going to specify, okay? So for example, if we have a second order differential equation, we have to specify two boundary conditions. We could give the initial position and initial velocity, and that will give us one form of the Green's function. Or I could give you the initial and final positions, and that'll give us a different form of the Green's function, okay? So this argument that the Green's function just comes from the operator is kind of crap, because you have to specify what boundary conditions you're going to supply, because they actually are reflected in the form of the Green's function, which we found two different Green's functions to the same differential equation last time based on giving different boundary conditions. Now, one more note, and that is we might consider, because all of the differential equations that we've been studying so far have just been differential operators, derivatives of x acting on a function of x equals a force function of x. But one might consider a differential equation of this form. First thing I want you to note is that this is not easily transformed into an integral. Okay, remember that what we did in the last few examples was we took something like that, and then we just took basically the derivatives of this, and we shifted the dx over to the other side. We integrated this left-hand side with respect to y, integrated the right with respect to x, and that's kind of the basis of the solution. But here you can't do that because you've got x and y mixed up in the force function. So it's not obvious how to turn this into an integral equation, except we found Green's functions. And it turns out that if you have the Green's function in hand for the operator L, you can apply it to this force function as well. And so if we apply the Green's function that we find for the operator L and integrate it go away. There we go. And we integrate it over the force function as a function of x prime and as a function of y, which itself is a function of x prime. Then that'll give us an integral solution to the differential equation. Okay? So Green's functions are in general a very nice method for transitioning differential equations into integral equations. It doesn't necessarily make them trivial to solve because you've still got to do integrals, right? But nonetheless, in many instances, it'll make solving a problem easier. Now, in one dimension, which is what we've been focusing so far, it turns out that there is a method you can employ to find Green's functions associated with operators, and that's really just to solve this equation. Okay? Because solving that equation is actually straightforward in the one-dimensional case. However, that method, which is shown in the book, okay, so if you're really curious and you're always finding yourself stuck with one-dimensional equations, maybe that's a method you should learn, but that method does not generalize to higher dimensions. So in moving up to 3 dimensions now, we're not going to be able to follow that method. We're actually going to have to go back to the details of how we derived the Green's functions in the examples that we did. All right, so let's go to 3 dimensions. in 3 dimensions, things get harder, obviously. Okay. And so what we're going to have to do is we're going to have to relegate ourselves to a smaller class of operators. You can't just use any old operator because first and foremost, you can't approach this as LG equals a delta function. But it turns out that even though actually being able to find the Green's functions for operators is limited to a certain set of operators, it turns out they're physically relevant. So let's consider the following operator. Okay. Where del squared, if you're not familiar with it, it can take many different forms. Here's a generic form. We can think of it as del dot del phi, where phi is a scalar function. And it actually can be written in general in the following form. 1 over h1, h2, h3 times the partial with respect to 1 of h2, h3 over h1 d1 phi plus d2 h3 h1 d2 phi plus d3 h1 h2 over h3 d3 d phi or d3 phi, where these h's actually arise in the following expression for the metric that we're using to describe our space. All right. I will write down explicitly what this operator looks like in one coordinate system if you do another. I'm going to do x, y, z. Ha ha! Hey, you guys are so quiet. Say it again.
I just said, let's discuss.
So if I do x, y, z, then it's just dx squared plus dy squared plus dz squared. The h1, h2, h3 are all 1. And this dramatically simplifies. Who'd like to do hypertoroidal coordinates for me? Sam. Are you on, Sam? Yeah, Sam, you're on. Can you tell me the form of this operator in hypertoroidal coordinates?
I'm afraid I can't.
I just made that shit up. I have no idea what it is. At any rate, yeah. So, but hopefully you're aware that, you know, if you want to do it in spherical polar coordinates or whatever, you just write out the form of the metric in those coordinates and then you just strip off your coefficients and do it. Anyway, I'm not going to go there. I'm just going to work with more abstract vectors, but here we go. So the equation that we want to consider is h naught on some function of a vector. Now I'm calling this vector r, but this is arbitrary coordinates. So this is not necessarily spherical polar coordinates. It's just the position of the object that you're considering. Equals f of r. So there we have our differential equation. And can Seth, no hypertoroidal coordinate, Seth, just a question. What was our first step in approaching this in the last lecture? We were going to try and find the Green's function for that more general operator, and the very first thing that we did was we did a little bit of a transform. Do you remember what transform we used?
No, I do not.
Anybody want to help him?
Do we use a Fourier transform?
Yes, we used a Fourier transform. So that's what we're going to make use of here. We're basically going to walk down the same alley that we did in the last lecture. So hopefully this will be sort of a review of those concepts in a slightly more complicated context. But we're going to hit some things along the way because we are working in 3D, which is going to make it a little bit more challenging than last time. Here we go. Here's our Fourier transforms. So we Fourier transform the field phi, and that's going to give us phi as a function of the vector k. The 1 over root 2 pi, of course, gets advanced to a 1 over 2 pi to the negative 3 halves. But the Fourier transform pretty much looks the same. You just have to promote everything to vectors. Okay. And then, of course, we'll have the Fourier transform of the f function as well, and it's largely going to take the same form. Now remember, the form of D3R, the measure of integration, that's going to depend on what coordinates we end up using. And we will adopt a certain set of coordinates to do a few integrals later on, but this is a very general expression. I'm not restricting myself to any particular set of coordinates. Okay, if I take these Fourier transforms and dump them back into the differential equation, then what we're going to get is the following. So this is going to descend to 1 over 2 pi to the 3 halves integral e to the minus k dot r del squared of phi d3r. Okay, so that's this term right here. Lambda is just a constant, so lambda is just going to multiply phi, so we can just go ahead and slap in the Fourier transform version of phi for the lambda term. So this is just going to be lambda times the Fourier transformed version of phi. And then that's, of course, equal to the Fourier transform version of f. Do you follow what I just said? Okay, good. Now, in our previous cases, we had to do an integral like this. And what did we use in evaluating integrals like that in our previous cases? Say it loud, say it proud.
Oh, did we essentially use spherical coordinates?
Well, no. So we have an e to the minus ikr times the derivative of something.
Oh, integration by parts.
Yeah, we used integration by parts. So we can actually use integration by parts in this three-dimensional context, but integration by parts in this context has a slightly different name. It's called the Green's theorem. And the Green's theorem, in case you don't remember, and you might not remember, looks something like the following. The integral over a volume V of f times del squared of g minus g times del squared of f integrated over d3r is equal to the integral over a surface of f del g minus g del f dotted with the normal to the surface times the differential surface element. Okay? And the idea here is that the surface S encloses the volume V, and the normal n points out of the surface. Okay? Now, I will talk a little bit about normal vectors at the Society of Physics Students meeting tomorrow. But for tonight, we're just going to keep it simple. So we just imagine this bounding surface, for example, being a sphere. And in that case, it's obvious what's in and out, and the normal vector points out. And so we can take this and we can rewrite the integral here. And what we're going to get is the following. 1 over 2 pi to 3 halves integral over the volume of e to the minus I k dot r del squared phi as a function of r d3r is 1 over 2 pi to the 3 halves integral over the volume of phi, and notice I'm just moving one of these terms here over to the other side. phi of r del squared e to the minus ik dot r d3r plus 1 over 2 pi to the 3 halves integral over the surface of e to the minus ik dot r del phi minus phi of r del e to the minus ik dot r. Oh man, I'm running out of room. Dot n hat ds. There we go. Okay. Now, I have a question. Andrew will happily answer it. Andrew, what volume V do you think we're considering in trying to solve this differential equation?
That's a good question.
So let me ask you the following question. You're used to doing this in geometric context where you have a spherical distribution of charge, you have a cylindrical distribution of charge, and then you take the volume integral and you relate it to the surface integral or whatever.
Sure.
This is a function which is defined everywhere throughout space. And so we're trying to do this integration by parts. So what volume do you think this involves?
All space? I don't.
Yes.
Yeah.
Yes.
Okay.
So what surface do you think it involves? What surface encircles all of space?
A big one. I agree with that. Let's go with that.
Yeah. So let's say you went to spherical polar coordinates to describe
Sure.
it. What would you take R to be?
R, the infinity? I don't.
Yeah.
Okay.
You're talking about if you want to use a spherical polar coordinate description, you would just be taking a sphere of radius infinity. That's the
Right.
surface which encompasses the volume, which is all of space. Okay, you on board?
Yes.
Okay, good. So we have a sphere of radius r goes to infinity. And remember, our normal vector in this case is just the radial normal vector. So what do you think this becomes if we take r to infinity?
I think it'll become 0 if we're assuming that the function vanishes sufficiently quickly.
Yes. This will go to 0 if phi of r goes to 0 faster than 1 over r. Okay? Now, we're actually going to find this is a property of the solution for phi of r. Okay, but that's going to come in time. What? 544. Okay, all right. So then if we do that, then this guy is just going to become 1 over 2 pi to the 3 halves integral over v e to the minus ik dot r del squared phi of r. Well, that's just going to be minus k squared times the Fourier transform of phi. Okay. Because if you think about it, if you're taking the derivative of e to the minus ik dot r, if you're taking it twice, you're pulling down the factor of minus ik twice. So that's going to give you minus k squared times the function you started with. All right. But the function you started with was the integral over the volume of phi r e to the minus ik r, but that's the Fourier transform of phi. So at the end of the day, this is going to give us for our entire differential equation something like minus k squared plus lambda times phi hat of k. Oh, goodness. It's something about being near the bottom of the screen that's triggering it. But at any rate. Okay, there is the essential Fourier transformed version of our original equation. And this has that nice, lovely property that in order to isolate the thing we want to find, which is phi, we can use algebra, right? No? Yes? Can we
Yeah.
algebraically, can we algebraically reorganize it always?
I think with the Fourier transform, I think as long as it's a linear differential operator, I think you can algebraically reorganize it.
Well, I would say that this algebra is pretty straightforward and gives a really sensible answer unless something goes wrong. What could go wrong? Scott. No, Scott's not on. Scott's, yeah, he's somewhere else. Jacob. What about this could go wrong?
You could have lambda is equal to k squared.
I know. That will be a pain in the butt. Okay, so we're going to analyze that situation, but we're going to start with a simple situation. And the simple situation is just to consider that lambda is less than 0, in which case the denominator of this will never vanish. All right. So let's take for lambda less than 0, how our story plays out. Okay. And I'm going to do some steps here, which I'm going to repeat in the following case. But I'm going to do them in detail now, and then I'll go through them more quickly in our second analysis. For lambda less than 0, let's first of all, let's call lambda minus eta squared. Okay, the square is just for convenience. Well, actually, no, the square is just forcing this to be a negative contribution because eta squared is obviously a positive number, and then you put a minus in front of it. This is our condition that lambda is negative. Then we have our equation becomes phi hat of k is minus f hat of k over the quantity k squared plus eta squared, where of course the denominator of this never goes to 0. And now what we're going to start doing is undoing Fourier transforms, because we are interested in phi as a function of position, not phi as a function of k. Okay, and we also want to express things in terms of f as a function of r, not f as a function of k. So we're going to start undoing these Fourier transforms, starting with the one for phi. So we're going to have phi of r is lambda of r, and I'll come back to what lambda of r is in just a minute, minus 1 over 2 pi to the 3 halves integral, and we're going to use f hat of k hat, or f hat of k over kappa k squared plus eta squared. In the book, when he did this, he used k and kappa. Instead of eta, he used simple kappa, and I found his expressions ridiculously hard to figure out because it was k squared plus kappa squared. They look exactly the same to me, and I thought about giving you that lecture, but then I was like, no, it'll be nice. Anyway. All right. I'm glad you guys are laughing out loud, because now I know I'm funny. At any rate. Okay. All right, so first of all, what do you think this is? Danny. Are you on, Danny? I'm looking for Danny. Oh, Danny's on. Nice. Danny. Daniel Moore. Daniel Moore's name is down there, but he's very silent. Joel Bean. You had to scroll through all of these. What do you think that lambda is?
One thing that's
confusing me is the fact that we have two lambdas, but I think that this lambda is
Oh,
some
shit.
sort of arbitrary-
Yeah. Oh, well, no. But this, in this form of the solution, we're calling that, we replace lambda with eta. So I'm using a variable.
So they're unrelated.
Sorry about that. So actually, it's funny. It's actually really funny, and I'm going to explain this to you. In the book, he, instead of lambda, uses this crazy ass symbol, psi or xi. But anyway, I can't draw that quickly enough, so I just replaced it with a very easily drawable symbol. So that's why I switched it to lambda. But in the book, it's this symbol. But anyway, all right. Anyway, carry on. What is this? What is this function supposed to be?
So it feels like this is some arbitrary function that fits some criterion. It like it might be 0 when you take the Laplacian of it, but I'm not quite sure.
Yeah, so actually what we're going to do is we're going to do the same thing that we did in our previous solution, which is we're going to add on solutions to the homogeneous equation, and we're going to allow those solutions to help us satisfy boundary conditions. So we want this to be a solution to H naught lambda of R, which is of course del squared minus eta squared lambda of R, and we want it to be homogeneous. We want it to be 0. Okay. Now, an obvious solution to this is pretty straightforward. It'll be e to the plus minus I times n times the magnitude of R. But we want only solutions which go to 0 as R goes to infinity. Okay, that was a condition we were imposing on our main solution. It's also going to have to be imposed on these homogeneous solutions. Are these functions going to go to 0 as R goes to infinity?
No.
No. Okay. So we are going to set lambda of R to 0. We're going to say we don't have any solutions to add on. This will be different in the following story, but for this case, there are no solutions to the homogeneous which die off at infinity. Okay. So with that in mind, our phi of R, we can write it as the integral of the Green's function times the force function integrated over d3 prime, where g of r prime, is minus 1 over 2 pi cubed times the integral of e to the ik dotted with r minus r prime over kappa squared plus eta squared d3k. Okay. This is just plugging back in the Fourier transform, the Fourier untransformed version of f, and then identifying what's playing the role of the Green's function. Now, we got to do this integral. Let's do this in steps. And I'm going to go through this in a lot more detail than it was done in the book. The integral that we need to do is essentially this guy. Oh man, what a pain. Oh, well, you know what I'm trying to write. Okay. And this is where we will at first find it convenient to break this into a specific coordinate system. So we'll use spherical polar coordinates. And hopefully you're somewhat familiar with how this thing will break down if we shift it into spherical polar coordinates for the k. So we'll first of all have an integral from 0 to 2 pi of d phi. That's the innocent integral that really doesn't touch anything else. We've got the integral from 0 to pi of sine theta d theta, and then the integral from 0 to infinity of k squared e to the I k times the magnitude of this r vector minus the r prime vector, cosine theta, because there's a dot product between the k vector and the r minus r prime vector over k squared plus eta squared. And that's integrated over dk. Okay? I'll do one of these if you do the other. Done. Oh, let's see.
The
Josh.
integral. Oh, sorry. Can I go?
No, I'm gonna let Josh do this.
Okay,
Josh,
sorry.
how about you do the second
me.
integral with respect
All
to
right.
d theta? Josh.
Does that include the gross 0 to infinity integral?
Well, I mean, the integrand of the gross integral from 0 to infinity does have a
wait.
theta in it. It does have a theta in it.
But isn't that the Dirac delta? Oh wait, no, there's the k on the bottom.
Mm-hmm.
K on the top.
How are you gonna do this integral?
With help from my wonderful professor.
Really? You should go get him.
Hey Joel.
Okay, no, I'm gonna walk you through it. I'll walk you through it. It's not that bad. It's not always obvious how these things work. Okay, so we're going to take this and we're going to define cosine of theta as some quantity t. All right. And first and foremost, that gives us that minus sine theta d theta is equal to dt. So that's nice because I get to replace this integrand here with dt, and this cosine theta in the exponential just turns into a t. So this is literally going to be the integral over e to the t, or e to the kt. Everybody understand what I just said? Now, the initial condition, which started out at theta equals 0, is actually going to be 1. And the final is going to be minus 1. So if I do this, if I plug this in, and I'm going to give you the steps. I'm not going to just beat you over the head with it. If I do integral minus 2 pi, integral from 1 to minus 1, dt times the integral from 0 to infinity of k squared e to the I k r minus r prime t over k squared plus eta squared dk. Now, can you do that integral with respect to t?
It'll require a little bit of finagling, but I think so.
Yeah, yeah. I mean, it's just an exponential of t.
Yeah.
Okay. So I can write this as 2 pi over I times r minus r prime times the integral from 0 to infinity of, and I'm going to write these in the following way, k e to the minus, or k e to the I k r minus r prime minus k e to the minus I k r minus r prime. These two terms are just what you get when you plug in the 1 and the minus 1 limits. dk over k squared plus eta squared. Okay? Now notice you're integrating from 1 to minus 1, but there's an overall negative coefficient. So what we can do is we can take that overall negative coefficient and we can just swap the integral limits. All right? So you're actually going to integrate from minus 1 to 1, and you're going to ignore that minus sign that's multiplying the whole thing. But nonetheless, there you go. And now we can do something rather interesting with this. Notice, this is an integral from 0 to infinity. But as we're letting k go from 0 to infinity, this thing over k from 0 to infinity is exactly this thing over k goes from 0 to minus infinity. Everybody see that? I mean, I got a minus k and I got a minus k up here. So if I put in the positive values from 0 to infinity, that is exactly like taking this and putting in the negative values. So what that means is we can rewrite the integral. Oh, man. Ugh. I never do this with a whiteboard. We can rewrite this as the integral from minus infinity to infinity of k e to the I k r. And then let me get rid of this fancy thing. Okay. So we can get rid of this term by extending the integral limits from 0 to infinity to minus infinity to infinity. Does everybody follow that? Okay, good. I told you I was going to walk you through this very carefully. All right. Now we've got to do that integral. Hold on. So this is the integral over a real parameter k, but imagine that in integrating this from minus infinity to infinity over the real axis, we take this as part of the closed integral of k e to the I k r minus r prime over kappa squared, or over k squared plus eta squared dk around the following path. Okay. And we might take the contour counterclockwise just for fun. Now, hopefully I don't have to go through the details of this again, but if we take the limit that r, the radius of this path, goes to infinity, then the integral along this contour along the straight line, the real line, is exactly the integral we're trying to figure out. It turns out that the semicircle part of this closed path integral will vanish by Jacob's theorem or Jordan's theorem again. So the semicircle part is going to vanish by Jordan's theorem. All right. So basically, the closed integral around the entire contour is going to be equal to the integral along the real axis from minus infinity to infinity. But what is the integral around the closed contour?
Unless there are poles contained in the contour, it's going to be 0.
Are there poles?
No, because because m squared is positive.
Oh, really?
But don't you have?
Oh, there are poles on the imaginary axis. I'm sorry.
Exactly. K squared plus n squared equals 0 for k equals plus or minus I eta. So we have a pole here, and we have a pole here. Okay? So now, what is the closed contour integral of that thing going to be?
It's going to be equal to the residue around the pole.
Yes, it'll be 2 pi I times the residue. So let's take this denominator and let's rewrite it in terms of k plus I eta, k minus I. Oh gosh, this is driving me nuts. Go away. K minus I eta. Okay, that's the same denominator I had before. But now what I have to do is I have to figure out the residue of this. But remember how we do the residue? And now I'm not going to write this down. I'm just going to tell you the answer. We have this pole at I eta. That's this term right here that's giving rise to it. So to figure out the residue, we take the rest of the integrand and we evaluate it at that pole. This is using the Koshi integral formula. Okay. So we take everything else in this thing, so all of this, and we evaluate it at k equals I eta. All right. So if we do that, what we end up with is, for this integral, we end up with 4 pi squared over r minus r prime I eta e to the minus eta times the magnitude of r minus r prime over I eta plus I eta. That simplifies. 2 pi squared over the magnitude of r minus r prime e to the minus eta times the magnitude of r minus r prime. Okay? So at the end of the day, our Green's function, plugging back in everything, our Green's function is just going to be gr r prime is minus 1 over 4 pi e to the minus eta r minus r prime over r minus r prime. How many of you have seen this before? No takers?
Oh, that's the Fourier transform of the Yukawa. That is the Yukawa potential. Sorry, not its Fourier transform.
Yeah. So finally, if we want to figure out what our phi as a function of r is, remember we argued that lambda is 0 because none of those functions will vanish at infinity. This is going to be minus 1 over 4 pi times the integral e to the minus eta r minus r prime over r minus r prime times the forcing function integrated over d3 r prime. Okay. Now, I want you to try and follow the following argument because I found it a bit difficult. Let's consider taking the magnitude of the vector r, which is the argument of this thing, to infinity. Okay? If the forcing function f of r prime decreases rapidly enough, okay, we can say for the magnitude of r prime being larger than some number r, then this thing is 0. Then the integration over dr prime will give 0 beyond the value r prime magnitude equals r. Because you're integrating something times this function, and that function is going to 0 as R prime gets really, really large. Does that make sense? Now here's the deal. I just want you to realize this thing has two competing infinities, because you want to consider the limit as R goes to infinity, but you've got to figure out how does the range of integration of the magnitude of R prime going to infinity, how does that compete with it? And what we're doing is we're saying, no, we're not going to have an R prime goes to infinity contribution, because we're going to cut it off at a certain finite range. Okay? Does this make sense? So what that means is that what we have left as R goes to infinity is something that we would get from integrating the angular part of this story. It's not that important, times e to the minus eta times R over R. Because if you think about it, e to the minus eta R minus R prime, if R prime is only going to be contributing up to a finite amount, and then you're sending R to infinity, R minus R prime is just going to limit to R, and that's e to the minus eta R. Similarly for the denominator, R minus R prime is going to limit to R. Does this make sense? Now I will ask you, is this solution going to 0 faster than 1 over R?
Yeah.
Yes, it is,
Because of the
as
exponent.
promised. Okay. All right. So it is 6:12. I don't believe that I will be able to get through the alternative, which was, in case you don't remember, whether this thing had a pole or not. Okay. So we did get through the lambda less than 0 case, and at the beginning of our next lecture, we'll start out with the lambda greater than 0 case, and that'll be a nice review of these details. Fortunately, we won't have to go through them because they'll largely play out the same way, so I won't go through them that slowly. There will be a bit of a hiccup along the way, and you'll understand what that is when we get to it. But at the beginning of next lecture, we're going to go through the lambda greater than 0 case. We're going to find the form of the Green's function for that. We'll find the limits as R goes to infinity. And then we're going to take all of these results and we're going to apply them to physics contexts. Okay? And so hopefully we'll end this non-physical course with a little bit of physics discussion. But I think that's going to wrap it up for today, because I don't think there's anything that I can touch on this next set of material and get through in the next 2 minutes. So I think I'm going to let you go a little early. All right. And hopefully you got my email that said that I'll be holding office hours Monday night and then Tuesday during the day, in reflection of what I usually hold my Wednesday, Thursday office hours. But I just figure you might want office hours just before your quiz on Tuesday. All right. That's the end.